All right, today we're jumping into a real scientific detective story. I'm talking about a baffling phenomenon, a clue that just didn't make any sense, and it threatened to unravel everything we thought we knew about the very nature of light.
You see, for hundreds of years, physicists were pretty confident they had it all figured out. Light? Oh, that's easy. It's a wave. Period. Case closed. And you know what? That theory worked beautifully, right up until the moment it completely fell apart. A simple little experiment turned up a secret that was about to change, well, everything.
So let's start where all good mysteries do, at the scene of the crime. We're looking at this really puzzling phenomenon, a physical effect that the old rulebook, classical physics, just had no answer for.
Okay, so picture this. It's 1887, and a guy named Heinrich Hertz is messing around in his lab. He notices something kind of weird. When he shines high-frequency light, think ultraviolet light, onto a piece of metal, it literally boots electrons right off the surface. He called it the photoelectric effect. Makes sense, right? Photo for light, electric for the electrons. Seems straightforward, but trust me, the devil was in the details.
And this is where things get really strange. See, the old wave theory made a couple of predictions. It said that any kind of light, as long as it was bright enough, should be able to knock an electron out. You just gotta wait for the wave to build up enough energy. But what the experiments actually showed? The complete opposite. You could blast some metals with super bright red light all day, and nothing. Nada. But then, you hit it with even a super faint violet light, and bam! Electrons fly off instantly. The evidence just didn't match the theory at all.
So the case went cold. For years, the smartest physicists on the planet were scratching their heads. They were stumped. And then, in 1905, our maverick detective shows up. He comes in with this wild, radical explanation that sounds less like physics and more like sci-fi. And that detective? A young Albert Einstein.
Einstein's idea was just mind-blowing for the time. He basically said, hey, what if we've been looking at this all wrong? What if light isn't some smooth, continuous wave? What if it's actually a stream of little energy packets? He called these tiny particles of light photons. Okay, so his theory really boils down to three big ideas. First, like we said, light comes in these discrete packets, these photons. Second, an electron can only absorb one photon at a time. It's a one-shot deal. It's like a one-ticket, one-ride situation. And third, and this is crucial, for an electron to escape the metal, it has to get hit by a photon that has enough energy to pay a kind of energy toll.
And that toll has an official name. It's called the work function. You see, every metal holds on to its electrons with a certain amount of energy. To rip an electron out, you have to overcome that. The analogy here is perfect. Think of it like a cover charge to get out of a club. If the photon doesn't have enough cash, enough energy, to pay the cover, the electron is stuck inside. It's not going anywhere.
And Einstein, being Einstein, wrapped this whole idea up in one beautiful, elegant equation. It basically says the energy you get from that incoming photon gets split into two jobs. First, you pay the work function, that cover charge. Whatever energy is left over, well, that becomes the electron's kinetic energy. That's its speed as it zips away from the metal. And just like that, this one simple idea explained everything, why only high-frequency, high-energy photons had enough cash to do the job.
Now, Einstein's theory was brilliant. It was elegant. It seemed to solve every single piece of this puzzle. But you know how it is in science. A good story isn't enough. You need proof. You need cold, hard evidence. It was time to put this radical idea to the ultimate test.
And for about 10 years, that's all it was. A really clever theory with no solid proof. That is, until an American physicist named Robert Millikan came along. He decided, you know what, I'm going to settle this once and for all. He designed an experiment to measure the photoelectric effect with incredible precision. His goal? To either prove Einstein was a genius or that his theory was just a nice idea.
So this is the kind of setup Millikan put together. It's pretty clever. On one side, you've got light hitting a metal plate and knocking off those electrons. Those electrons then fly across a gap to another plate, the collector, and that creates an electric current. The whole point of this contraption was to do one thing and do it really, really well. Measure the exact energy of those electrons as they came flying off.
And his method was pure genius. So he'd shine the light, get the electrons moving, but then he'd apply an opposing voltage, basically an electric headwind, to push them back. He would slowly, carefully turn up this back voltage until the current stopped completely, meaning not even the fastest, most energetic electrons could make it across. And that voltage, the exact amount needed to stop them, the stopping voltage, gave him a perfect measurement of their maximum energy. It was like he was interrogating the electrons to find out how much juice they had.
So Millikan did this over and over and over again. He used different colors, different frequencies of light, and carefully wrote down all his results. He recorded every single data point. And when he finally plotted all of that data on a graph, well, he ended up with a chart that would literally change physics forever.
And this is it. This is the evidence he collected. Each one of these dots is a single, careful measurement. Along the bottom, you have the frequency of the light he was using, basically the color. And going up the side, you have the maximum energy of the electrons that he measured for that color. This is the raw data.
Now, if you just look at it, it kind of just looks like a bunch of dots, right? But the real magic in science often happens when you find the pattern hidden in the data. So what happens when you try to draw a line through them?
Bam! A perfect straight line. I mean, look at that. This was the smoking gun. You have to understand, in the real world of experiments, things are usually messy. Getting a result this clean, this perfectly linear, it's like finding a signed confession at a crime scene. The data wasn't just whispering, it was shouting.
And this line wasn't just a pretty pattern, it was a treasure map packed with secrets. The steepness of the line, its slope, that turned out to be a fundamental number in the universe called Planck's constant. The spot where the line crosses the horizontal axis, that tells you the exact minimum frequency you need to get any electron out. And where it hits the vertical axis, that's the metal's work function, the exact cover charge we were talking about. It was all right there.
And here is the mic drop moment, the final, undeniable piece of evidence. If you take the equation for the straight line that came from Millikan's actual real-world data, and you put it side by side with Einstein's equation, which was pure theory, they're the same. They match perfectly. The experiment confirmed the theory, down to the letter. Einstein was right. And in proving it, they had found a crack in the foundation of classical physics that would blow open the door to a whole new world, quantum mechanics.
I mean, what a monumental discovery. It confirmed that light has this bizarre dual nature. Sometimes it's a wave, sometimes it's a particle. And it kicked off the quantum revolution. But this story doesn't just end in a textbook. No, this discovery has practical applications all around us. This fundamental understanding of how light and matter interact is the core principle behind so much of our modern tech. You know, solar panels turning sunlight into electricity? That's the photoelectric effect. The sensor in your digital camera? Same thing. Even those automatic doors that open for you at the supermarket? Yep, you guessed it. All of it goes back to this.
So there you have it, our whole detective story. It started with a bizarre puzzle that old-school physics just couldn't crack. Then came a totally radical theory from one of history's greatest minds. And finally, a meticulous, painstaking experiment delivered the knockout proof, which ended up changing technology forever. It's just such a powerful reminder, isn't it? How one single nagging question can spark a total revolution in science. And it kind of makes you wonder, what other fundamental ideas, things we just take for granted today, are just one brilliant experiment away from being completely transformed?